Okay, I think we can start. Welcome everyone to the strong lensing session. So we will begin by the reminders.
You might want to use a microphone. I can't hear you this close.
It's on. Hello. Can people hear me with this?
No.
On Zoom, yes.
It says on. Hello. Can you check whether
It's not possible. It's only for Zoom.
what?
There's no internal amplification.
I think you need to come closer. We can swap. If you want.
That is only possible. Okay. Yeah. Okay. Yeah.
So, but also that means we should use it so people on Zoom can hear us.
There's
there
a
are
microphone
internal
over here.
Oh, okay, just for, okay.
It's only for the
That side of the room.
yeah.
So that people on.
Oh, you want to come here, speak with me?
Okay, I'm going to try and speak loudly.
She's
So
gonna speak loudly.
we will begin with the reminders. So first, we have the code of conduct and some instructions on COVID-19 protocol. People are also encouraged to remember that there is social batteries. You may want to think about interacting with the people. Another set of reminders is virtual participants are requested to stay on mute, and in-person participants should speak with the room microphones that would be circulated. And yeah, we have a few talks which are going to be on, like at least one talk which is on Zoom. So please use the standard procedure that we follow for Zoom and online participants. Here's just a brief summary of the various talks we're going to have in this session. The virtual participants, they can write their questions in the Zoom chat or you chat to request to unmute. There's also a dedicated Slack channel for this session, so please post your questions there. And we have Prajakta here who's monitoring the session, and she can ask questions on your behalf if you're not able to join or speak during the session. So with that, we can start with the first talk in this session.
Yeah, so the first talk is by Anuprita, and the talk is on the Rubin Static Strong Lensing Data Challenge towards automated discovery and modeling at LSST scale.
So thanks. Hi everyone, I'm Anuprita More, and I'm going to talk about this Rubin Static Strong Lensing Data Challenge. So this is on behalf of the organizing team, and you see the names of the members listed here. The challenge website is also shared here, which has information on different aspects of the challenge, including some of the results, extended set of results. So the idea behind the challenge is as follows. Our goals are to develop machine learning models and methodologies to detect strong gravitational lenses, to identify strong gravitational lenses with high precision and recall, to minimize false positives while retaining subtle lensing features, and to develop models that can handle LSST's unprecedented data volume. The challenge is organized into 4 phases. The first phase was to set up the challenge design and data sets. The second phase was to actually generate the data sets. The third phase was data set validation, feedback, and finalization. And the last phase was the launch of the challenge. Regarding the challenge design and dataset features, the idea was to simulate 1 year LSST survey data and look at 4 different bands, GRIZ. There were 2 types of datasets that we were working with. One was pure mock LSST datasets, and the other was making use of real HSE datasets, but then degraded to match 1 year coad of LSST. There were other considerations also in the data sets. For example, there are 2 types of classes that we are generating. One is the strong lenses and the other is non-lenses. And the plan was to create diverse set of realistic parameter space in this data set. And we had also developed a degradation pipeline, which was run on the HSE survey data to then create LSST-like images. So here's just a brief overview of the degradation pipeline that was developed for this purpose. On the top left, you can see how the original HSE image looks like, then the degraded version, and then the third panel shows the degraded with the noise added. On the right-hand side, you can see the overall workflow, which shows where the different parameters or important factors that went into consideration to try and match the HSE images to that of the LSST. And then on the bottom left, there are some of the other details of these parameters. For the sample of lenses and the non-lenses, we are showing here on the left-hand side the various parameters which were set for defining our lens samples. Since we had two different kinds of data sets produced by two different pipelines, we wanted to have some sort of uniformity in these samples. So that's the reason to also set up this kind of different parameters and defining the sample of mock lenses. On the right-hand side, there's description of the different types of non-lenses that we considered, which include both simulated and real non-lenses. Again, selected from the real HSE and then also generated from the pure mock LSST data sets. Here in this slide, I'm showing the like an example gallery that was produced both for non-lenses and lenses, which is shown by the column, and then the rows show the degraded HSE sample on the top, and then the mock LSST sample in the bottom. So I would like to show some preliminary results. So first, I'm showing the results from the searches. So when the challenge was launched, there were about 20 teams who participated in doing the lens searches. And on the bottom left, you're seeing the standard ROC curves, which shows the performance of these various 20 networks or pipelines that we received the results from. And then on the top right, we are showing the predicted, we're showing the magnitude of the arcs and on the y-axis and the Einstein radius of the lenses on the x-axis. And each of the cells, they show the fraction of the detections that are, fraction of the lenses which are detected by the pipelines. So the left panel shows from the top performing network, and the middle panel shows the best, the top 5 network performance. On the right hand side, we have an ensemble network that was created on the basis of on the basis of combining some of these best or the top 5 networks, and it shows the performance from that network. And some of the other metrics are also listed here in the table, which you can refer to later. The second part of the data challenge included results from or analysis from the lens modeling part. So here we received contribution from 5 different teams. On the right hand side, we are showing the performance where the x-axis shows the true parameter and the y-axis shows the predicted parameters from those networks. And each column represents one network. So you can see how the different parameters, like for example, on the top, you can see the Einstein radius, which is one of the very important parameter that needs to be predicted by the network. And you can see that many of the networks are able to predict this parameter very well. On the left-hand side, we are showing, so this is all the analysis on the test data sets, which mainly includes all the simulations. Whereas on the left-hand side, we have results on the 10 real lenses, for which we also have predictions from other studies in the literature, which are not necessarily machine learning based. Some of them also include very detailed and accurate mass modeling done with the conventional MCMC methods. And so you can see how the different parameters predictions compare from the different works. So in summary, I would like to say that we have conducted the first Rubin Static Strong Lensing Data Challenge. with the goal of providing realistic and diverse data sets of lenses and non-lenses, and benchmarking various lens finding and modeling algorithms, and also the goal of identifying accurate and efficient pipelines, which can be then run on the LSST data. For the lens searches, we had contributions from 20 teams. For the lens modeling, 5 teams participated, and we were able to do a systematic evaluation and comparison in this work for all these different pipelines. And in the future, we hope to identify some of the best or some ensemble network, which can then be run on the DP2 data. We also plan to conduct a version 2 of the challenge, which will then include data sets which are prepared with the real LSST data, and hopefully that will be in preparation for the like more realistic preparation for DR1. And our paper is in preparation and will be circulated soon within the SLSC. Thank you.
We have any questions for Anuprita?
I would have liked to have participated in the challenge, and I went so far as to get the data for the challenge. And then I discovered that you didn't provide the PSFs that went with the images. And in order for me to analyze images, I need to know what the PSF is.
Is this for the lensed AGNs?
I can't hear you.
Is this for the lensed AGNs or the PSFs that
You had a lens challenge. You distributed 20,000 frames.
Yeah.
But you didn't give the PSF. So
This
with
was-
which you generated it. You know, and the project gives you a PSF. And it makes it a lot easier to analyze it if you know what the PSF is.
I think we could provide that if someone had asked for it, but there was no requirement, like no one asked.
Well,
for
you
it.
gave us only about 2 weeks to do it. And by the time, so I wrote to both Pedro and Clesio.
Yeah.
And they said, we'll do it next time. But I couldn't participate because you hadn't provided the PSFs.
Okay, the challenge was running for several months, meaning the discussions about the challenge was happening for several months.
Discussions were happening, yes.
Yes, and in those discussions, we could have received the request for the PSF and
I
that,
didn't participate in those discussions.
yeah, so we can do this next time then.
And as sort of a bystander here, Paul, wouldn't it be more realistic though to actually approximate your own PSF for the lens challenge images? Because after all, there is some error anyway between the LSST PSF and the true PSF of the system. And it would seem like one should capture that impact in the lens challenge after all.
So as a second order, you're quite right. And you know that Abi Saha, for example, has an idea of you try. Second order, indeed, you can improve upon the PSF that's provided by the system. And Abi is thinking about that. But first order, please tell me what the shape of the PSF is. You know, just an ellipse, that's enough. And then I can improve upon it if need be. But for the point of view of identifying things, it's not a big deal.
So we also had a mini challenge released before the actual challenge that also gave sufficient time for people to look at the data and again, either report any issues or make any requests. So I think there was sufficient time that went by before the actual launch.
I got an email from I'm part of the collaboration. I got an email and it says it's due in 2 weeks. I downloaded it and there weren't PSFs. It was kind of late to be generating those things.
Okay. We have most of the discussions on the Slack channel, so that's where we get all the inputs and feedback from. So this is like a specific requirement. So if you have that requirement, then
I think everybody needs the PSF when they're analyzing images. I don't think I'm unique.
but not everyone needs to use the same PSF. Like Gautam said that
Use
you
Use whatever PSF, give us
So-
whatever.
I'm gonna interrupt. Maybe Paul, you should take these questions offline. I think probably you've made your point. You've got an answer. If it didn't satisfy you, maybe you're gonna need to deal with that. I would say let's move on. Okay, I think you should probably stop at this point.
Charlotte had a question.
Oh,
Sorry. Yeah, I was just curious to ask about the various different modeling algorithms, like the extent of the variety between them, and if any of them were more effective for finding certain kinds of lenses, like different separations or
Did you say modeling or?
yeah, the different algorithms that were being tested.
Yeah.
I was just curious to hear about the variety of algorithms that were tested and if any were good for finding particular kinds of lenses relative to others.
I may not be able to answer all of that in this right now. Let's move on to the next talk and I can discuss with you.
Okay. So the second talk is by Margarita Grespan, The Promise of Self-Supervised and Active Learning for Strong Lens Discovery, Anomaly Applied for Kids.
Yeah, they got it out. That's theirs. That's her slide. Yeah.
Hello, everyone. I'm Margarita Grespan, and today I will present my work about finding lenses with astronomically private in kids. So let's address the elephant in the room. So why did I use kids? Well, kids is a good testing ground for lens finding, but also for Rubin in general, because it has the same pixel size of Rubin, so 0.2 arc-second, and a similar depth, so in R band. The data that I used for this study is the kids DR4, and I pre-selected 4 million bright galaxies out of it. So I will be mentioning all this kind of machine learning in my talk, so I just wanted to briefly overview them. So supervised learning is the one that I believe everyone knows of. It's when you have a model that gets trained on some label data, and then you get some prediction out of it. Unsupervised learning, you use model that can find patterns in the data directly without the use of labels. Self-supervised learning is when there's a model that automatically creates labor for training itself. And then active learning is when there is the human in the loop. So basically, labels are given interactly to the model whenever the model asks for it, basically. So lens finding, it's really important, as Anuprita mentioned, and all the current searches for in surveys are basically using machine learning as of now. Why? Because it's a needle in a haystack problem. So for instance, in Rubin, and within the 20 years of the survey, we're expected to observe 20 billion galaxies, out of which 100,000 will be galaxy-galaxy lenses. So in order to find these objects, we need to have good machine learning models. The other thing about supervised approach is that they are inherently biased towards the training set because they're being trained on it, and we use simulations as Anuprita mentioned because we don't have enough real objects to train our models. So in this work, I started by using self-supervised learning. So basically, I use this method that is called BYOL, that stands for Bootstrap Your Own Latent, in which I just take a pre-trained model, in this case a ResNet, which has pre-trained on terrestrial images, that means cats, dogs, cars, and then I fine-tune it to kids' data. How does this model or this approach do that? So you get one image, you create 2 different representations of these images, and you feed it to the same architecture, and then you minimize the distance in the feature space. So basically extract features with this ResNet, which is a convolutional neural network, and you get the most representative information out of it, and this is what feature extraction is. And you lower the dimension of your data in this way. So you basically start from your images, then you have your model, and you can get something that looks like this feature space. This is the full kids DR4 feature space, and in which every point is a bright galaxy. So you have further decrease your dimensionality by using other approaches like PCA and UMAP. But let's get going. You can also visualize your UMAP directly with your RGB images, so you get something like this. This is a spoiler, so let's not talk about it now, the red boxes. So here's where I use active learning. So I have my feature extractor, I have my feature space, and I need to understand where my lenses lie in the feature space. So I get this model that asks me to labels of lenses, and when to do this, I use Astronomaly, as I mentioned earlier. So it basically shows me one image, then I give a grade, and if it's a lens, I will give 5. Otherwise, if it's something that looks like a lens, I will give a lower grade till to 0. So these are some example grades. So the first row is 0, then you get 1, 2, 3, 4, 5, and you see that the objects tend to like look more like lens-like the higher the grade is. So you label, and 3,000 label later, you had some candidates, strong lens candidates. So these are the objects that the model showed me within these 3,000 labels. The red boxes are the objects that are known in literature, so that have been found before within kids. So the first object is, of course, an Einstein ring, and is known, but it hasn't been found in kids but in other surveys. So I didn't highlight it. So within this active learning approach, I found 34 grade A and B, and then around 150 grade C lenses. So AB is like what we are highly likely to be lenses. But then I asked myself, can we further exploit our feature space? Because 3,000 label is really not enough. So I decided to use similarity search. So I take every candidate as a query and I look into this feature space within the 512 nearest neighbors. So this is the image I showed before. The red boxes are where all the lenses lie. So we can see that they all lie in like one bit of the feature space, which is really good because we don't have to explore it fully to find our candidates. In order to navigate the neighbors, I made this ad hoc app, let's say. So you basically interface where you just click and you give a grade to your candidates, and in this way you can it's a really fast way to inspect a high number of objects and just highlight what you like or what you don't. So these are the candidates that I found during the nearest neighbor search. So I added on top of the previous candidates 106 new A and B candidates and around 900 grade C, and 60% of these candidates are new. So what does this tell me is that this approach is complementary to the supervised searches, because kids has been highly investigated with machine learning model, but we still found candidates, and they are different than the one that we found before. So I think this is really the what I would stress on for this work. This one is just an example query, and what I found with the query is the image on the left, and then the neighbors, the good neighbors that I find. So this is my summary, and this is my last slide. And I just want to mention that this approach should really be used within LSSC and within other survey as a complementary approach to supervised approaches. Thank you.
Yeah, nice talk. Do you have so there's a power spectrum of dark matter fluctuations, both theoretical and approximately observed. And so that stuff is all in the foreground. Do you have an opinion on how your unsupervised lens finder captures that complexity in the foreground?
Not really. It's really hard, like, to parameterize what is happening behind on this kind of approaches, because it's not supervised. If you have a supervised, you know what you fit to the models and you know why something is happening. This is like future work. I'm really trying to investigate what is happening in the background. But thank you for the question. I'll write it down and try to figure it out. Thank you.
Let me take a shot at answering Tony's question. In the first instance, unless it's right on top of the first lens, it'll give you a shear.
Yeah.
And these models include the shear, basically. So if you want the ultimate model for that system, go back and model it properly. But from the point of view of finding things, I suspect that so effectively including the shear is good enough.
Do we have any more questions? Yeah.
It's a really nice talk. Thank you. Can you say something about the known lenses or existing lens candidates that you didn't find, if there were any?
Yeah, I did check why some were missed. In some cases, the feature extraction went wrong. I know they also use like Sigma clipping, so some observational cutters were really noisy. So basically everything got clipped out. So that's why I'm not using Sigma clipping anymore, to just make sure this doesn't happen. But beside that, I'm not really sure why. I think it's because like lenses are so diverse that basically if they don't cluster together, it's really hard to find them, because just the cost function is not like, since you're labeling just 3,000 label, if something is far in the feature space, you need some label to get to that far bit of the feature space. So I think that's mostly why it happened, because we're a bit farther away from where the rest of the lens is clustered. But I'm also investigating the SNR if that had some impact on it. Yeah.
I think we can let's thank Margarita again. And so next we're going to hear from Prajakta, and she's going to tell us about the DI pipeline and work on the lens transients.
Okay, hi, good morning, everybody. My name is Prajakta. I'm a 2B second year grad student at the University of Pittsburgh. And I'm going to be talking about my work on testing the LSST difference imaging analysis pipeline to identify strongly lens transients using synthetic source injection. So since this is the first talk on lens transients in this session, this is just like a brief intro to lens transients. So this is a diagram showing strong lensing of a point source. And if you imagine the source to be like a transient point source, and there's a foreground massive galaxy, we'll have multiple images of the same point source. And these multiple images will appear on the sky at a certain time difference. And using that time difference, we can constrain the Hubble constant and other cosmological parameters. Using these things, we can also get valuable constraints on the lens model if we assume cosmology. And finally, because transients particularly fade away, after they fade away, we will be able to get direct observations of the lens or the host galaxy without the contamination from the source light, and that will increase the constraints on whatever quantities we are trying to measure, basically. And in the LSST, all transients that will be detected are processed through this pipeline called the alert production pipeline, where we have the calibrated exposure on which we run the image differencing task, which I'll come to in the subsequent slides. And on the difference image, we will then run the detection and measurement algorithm. And finally, we'll end with the DI pipeline task, which is just running the association task. And we expect these galaxy scale strongly lensed transient systems to have very small separations of the order of like less than 1 arc seconds to about 5 arc seconds. And the aim of this study then is to understand how these different stages of the pipeline, of the alert production pipeline, behave on such closely situated, multiply imaged strongly lensed transients, and then use that understanding to design methods to identify them in the alerts. So to do that, I'm using the DP1 COMCAM data in the ECDFS field, and I use the raw images and run all of these stages of the pipeline to reach the calibrated exposures. I'm using that particular version of the LSST stack for all of this processing and doing these runs on NUST using BPS. So in these calibrated exposures, then go my injections. I'm currently doing only controlled injections of 2 closely situated point sources, which essentially mimic like a doubly imaged lens system. And these controlled injections are to allow testing over a large sort of range of separations and magnitudes, as you can see in the distribution over here. And we have kept the distributions like uniform by design. So then we do these injections in 2 sets. So firstly, we have injections at only empty positions in the sky. So here you can see an example where in the calibrated exposure, there is only there's no source. And then we are doing the injections at the locations of the plus mark. And the second set is injections on top of a massive red galaxy. So this is like a more realistic case. And you can see in the calibrated exposure, the galaxy, like the original galaxy, and on top of this, we have made these 2 injections. And on these injected images, I then run the difference imaging, which is, so you have the injected exposure and then template of static sky. So this is made by taking coadditions of good quality images of the same area of the sky. So you subtract the templates from the injected exposure to get the thing that has changed on the night sky, which is in this case, the things that have injected. And the plus marks are the locations of injections, and the circles are where the pipeline detects those things. And this is true for all other slides as well. And here you can see like the ideal case of recovery where we have 2 injections and 2 recovered sources. And I run this process on all of the injected exposures that I have. So these are some consolidated details regarding like the recovery. So on the left-hand side, you can see the plot of recovery fraction with respect to injected magnitude. And you can see sort of like an expected sigmoidal decrease in the recovery fraction as you go to fainter magnitudes. And at fainter injected magnitudes, we start losing both of the images, which is just like it's related to the depth of the image. The right side plot is slightly more interesting, where the red color bars are where we have missed the entire system. Orange is where one of the 2 injections were recovered, so it's a unresolved case. And green is the resolved case where both of them were recovered. And you can see around 3 to 4 arc-second separation, we start see increase in the systems that were resolved by the pipeline. As you may expect, it increases with the separation. But that plot alone does not cover the full picture. So this is the plot showing separation on the x-axis and magnitude, which is in the first plot on the y-axis. And now you can see in the third panel over here, the both recovered cases where the system has been resolved by the pipeline, sort of they come together in form of like a triangle or a corner at higher separation and slightly fainter magnitudes up to a certain limit, of course. And consequently, you also observe that even faintly separated bright systems are being blended by the pipeline. And yes, and as we understand that, that's because of their overlapping footprints. So I have a bunch of examples of cutouts and footprints over here, their respective footprints. So footprint are locations or like areas in the detection that are counted as part of the detection. And you can see in the first 2 set of images, 2 were injected, 1 was detected, and the footprint of both of them has sort of merged together, which is why only 1 of them was detected. In the third one, we now have slightly further separated sources and like slightly fainter sources, where now both of the footprints are separated and you can detect both of them. In the lower row, there are some peculiar cases where pipeline either like missed both of the images in the first 2 cutouts because of either like over subtraction of the galaxy or nearby bright object affected somehow. And in the third cutout, in the third set, we have detection that happened near the location of fainter injection. And you can talk to me why that's interesting later after the talk. And as promised, we are using this understanding to then figure out how to add, like what kind of filters to apply on the LSST alert stream to sort of pick out interesting candidates. And these are the 3 criteria, or like I guess 2 criteria that we are using. The first row shows extendedness of the detections. And the first panel is flux-based extendedness, where I compare the aperture flux and the PSF flux. And in the next 2 panels, I compare the shapes of the source and shapes of the PSF. In the bottom right plot, I am showing the color magnitude analysis, which is a method that works to identify lens type 1A supernovae specifically. And so we have implemented these 2 filters on alerts in the Google Broker, and we are monitoring these alerts. You can, I've made like a makeshift web page to share the candidates that are being selected by both of these methods, and you can like visit the web page and see the light curve, see the color magnitude diagrams and the cutouts of these things, and like wait visually and see if some interesting thing comes up. And in the ongoing work, we are trying to do large scale injections of entire light curves of like realistically simulated lens supernovae, with the understanding that we got from the fake kind of situations. And then we'll run this whole thing and try to get more catered filters using like lens supernovae, and then continue monitoring the alerts using the selection filters. And this project is a part of this work is a part of a desk project as well as proposed SLSC project. So feel free to join our project and like just come talk to me if you're interested in anything that I've shown. Yeah.
Questions?
Yeah, nice talk. That's injecting objects as a way to find your completeness function. My question is that you've shown us examples of objects that last for a while, like supernovae and kilonovae, which means that if you had multiple images of them during observations. And so my question is, have you looked into the possibility of using the multiple images in order to get around some of these issues?
Yeah, so I think the first issue that we are trying to tackle was the fact that the pipeline in some cases will not make multiple images out of these two things. So we're trying to understand at what stage it stops making two sources out of a blended system. And then next stage will be to, of course, then run association pipeline to see how that behaves in the epochs where all of the images or multiple images are present in the same epoch. So I have also done this on HSC, and so I have a couple of results from that. But now I will be doing the same thing on the DP1. So we'll have some more thoughts about that in the coming years.
Yeah, nice talk, Prajakta. Even if the DM pipeline is not doing the deblending right, is it possible to flag all of these sources enough in the alert stream that you can then go back to PPDB and do additional processing downstream? How many objects are we talking about?
Yeah, so currently, if you see over here, we have 700, don't I do it? Some 700 things that have satisfied both of the criteria. I am currently making some changes in this thing regarding some cross matching, which will make this number, get this number down to probably 300 to 400 until now. I also did talk with Ian yesterday, and he had some plans about adding deblender, simple kind of deblender. So that is also something that I'm working on. But we are exploring that possibility of going back and trying to run some deblending on just selected candidates. And the extendedness criteria is sort of a way to pick out interesting candidates, I think.
All right, let's thank Prajakta. And so the next talk is by Satad Rubag, and he's going to talk about discovering strongly lensed transients in the era of LSST.
Perfect. Yeah. So my talk actually continues endlessly with from Prajakta's talk. So I'm Satad Rubag. I'm a postdoc in Munich, and I'll be discussing broadly the direct search approach, but with a particular focus on one particular approach method. So what it is. So there are basically two broadly different approaches of finding lens transients. So let us focus on the first one. So this one. So this is watchlist monitoring. So before looking into the time domain data such as LSST, so you first gather all the known lensed candidates, known lensed galaxies, lens clusters in the footprint. Then you cross match the alerts. So suppose you get some alerts which are coming from the neighborhood of your lensed galaxies or clusters from your watch list, then you vet it. You carefully look at it and then decide if this is a lens transient or not. But the problem is that not all of the lens transients will have their hosts also lensed. That means they will never appear in these watch lists. And rough calculations tells you that half of the lensed type 1 supernovae in LSST will not be in the watch list. So for that, we need something else. So that is basically you directly look into the data and then you decide if this corresponds to lens transit or not. And there are, of course, multiple approaches. So Prajakta discussed basically the DIA-based approach. There could be color magnitude-based, also Prajakta, they have worked on. And the magnitude, so the magnification method has been proven successful because you expect that strong lensing makes your transient brighter. So suppose if you are seeing suspected supernova too bright for its suspected redshift, then you look closer. This might be a lensed supernova. And this method has been proven successful. There's also light curve, but I will particularly focus on the image time series method. But before going to that, I am coordinating the direct search in LSST, and this is the Slack channel, and we have very exciting and challenging problems to deal with. If you are interested, you can always join here. Now I will focus on the image time series. So of course we do not have, so one thing I forgot to mention, since we are dealing with the massive LSST alerts, I personally believe that there is like deep learning is inevitable. So you need possibly deep learning in every aspect. So now, yes, I'll be describing some deep learning based models, but before that, so we do not have real data to train, right? So we have to simulate. And here we took, we in Holy Smokes group in Munich. So we took this philosophy that we wanted to be as realistic as possible. So we do not build the training set from scratch. Rather, we ingested the real HSC, the hyper-super income data, which actually matches the LSST quality in many aspects. And then for the positive plus, we actually injected the supernovae at different epochs to made our time series. You can see that the spatial feature that evolves with time. And in negative examples, so we have different classes. So these are really exciting. I cannot explain more here. But I wanted to make one point very clear here. During this work, we had to deal with, since we are dealing with the real observed data, we had to make a time series out of a static observation. And we found some very self-consistent way to do this. So the main thing is that the PSF should vary over time, and you have to correct the variance map according to this. Okay, so this is my only slide with results and models and etc. So all I had shown here is basically in single band. Multiband, the scenario becomes much more interesting. So in multiband, the frames are not like they are asynchronous. So at a given point in time, you will have observation in general in only one band. On the top of that, you have to detect it early because you want to trigger the follow-up for confirmation, time to the estimation, blah, blah, blah. So your multiband time series looks like this. So the whole thing is basically one sample. So here, these blacks are basically the missing part. So the observation was only in this band here. So these four are basically, we chose 4 LSST bands out of 6. So now we actually trained 2 types of deep learning models. So the left side is based on RNN, the recurrent neural network. So it actually works sequentially, particularly the LSTM. And the results are really nice. So these are the ROC curve, but there are 14 ROC curve. That means each ROC curve tells you the performance after first observation, second observation, third observation, and you can see that they're improving. That means, so for example, by the 7th observation, we could detect like 60% of the lens supernovae at the expense of 10 to the minus 4 false positive. So this is basically our target. Now, so far so good, right? But the problem is that we always knew the limitations of the sequential model. So they are good, but so the problem here is that for this RNN kind of model, you need to fill up those missing bands. So see that you are carrying 3 times more zeros than like per observation. So this makes it like not so like forward facing. And we always knew that transformers will do the miracles here. So transformer can really work on this because it's based on attention. So you can think of any kind of attention that I will attend one part of the like one token to another one. And we got comparable results, actually better, but that is not the point. The main point here is that transformers are state of the art. That means a lot of development is happening there. You can take advantage of the higher end GPUs. And they're flexible. So as I was saying, you can think of many different ways to attend, and you are certainly guaranteed to get a solution of how much challenging problems you can think of. And so we thought that this kind of thing is a very niche problem for astronomy only. So I personally looked for years into the machine learning papers, and I didn't find any pre-built model to handle this. So that is why we thought that maybe it can help the broader community, broader transient community. This is my last slide. So although the title says that lens transients, but we till now, I think everyone I know, so we are basically working with type 1a supernovae because the light curves are much easier to generate. That needs to be extended. So in this work, extension means that you have to just inject the correct light curve. But this is much easier said than done. So we are working on this. The other part actually that touches on Prajakta's presentation also. So this model I described you, so it works on a time series where the center is not shifting. You can get this time series from the visit images, but that's like slightly impractical because the bulk download is not so easy. On the other hand, you get these small postage stamps from the alerts, but the alerts are not always, the center are not always fixed. So when we ran the LSST pipeline on this simulation, we can see that there are like fragmented dia objects. So this is also consistent with what Prajakta said. But the problem, so it makes the problem much more challenging and also interesting. So if you are just looking at this time series, so a dia object just means the time series, then you will be missing. So you will not be capturing the full story here. So you have to collect them all together. And we are also, we should be doing this. And DP2 is a milestone to adapt from HSC-like data to LSST-like data. So thank you.
Very interesting. How do you encode the time coordinate in the transformer-based approach?
Yes.
How do you use like some sort of different sinusoids, or what's the?
So you have to encode the time. We adopted time to vec. So this is like a time. So you represent the time into a vector and then you embed it with your position, like your spatial tokens.
Okay, thanks.
Any other questions?
Yeah, so regarding your first bullet up there, so you know the PSF from the stars in the field, so that's nice. But the PSF is going to vary quite a lot from one exposure to the other.
Yes.
Given that huge amount of variation, do you have a feel already for how much noise that introduces in this process and decreases your efficiency?
So in the latest training set, we actually varied the PSF, but we adopted the HSC. So you know that there's a small time domain part of HSC, and the PSF there varies, I think, more than LSST. And I cannot separate out that how much of the challenges this variation of PSF is creating, but it's not that big of a problem that we are seeing right now. But things can change with LSST. I completely, I'm open to that.
Okay, let's thank Satadru again. Top. Okay, so the next talk is by Paul Schechter, and he's going to tell us about lensed AGN or lensed quasar finding.
Test of an alert filter for on-the-fly modeling of quadruply lens.
Quadruply lens,
SNE.
supernovae.
Supernovae, yes.
So first, let me thank, in particular, Margarita and Prajakta for setting me up and explaining how one finds quadruply lensed systems in advance. So that will make my job that much easier. But here's something I ask you to remember, if nothing else. And that is that if a transient triggers an alert, it's likely to be a 5 sigma event and not a 6 sigma event. Because, as you go fainter and fainter, the numbers of objects rise and rise and rise. And so most of your alerts are always going to be right at the boundary. Now, If you have 4 gravitationally lensed images, other things being equal, you would think only 1 in 4 times is the triggering image likely to be the leading image. And so you've got a job of figuring out when the leading image occurred and where it occurred and going to look for it. And that's pre-covering, as people call it. So your alerts are all going to be 5 sigma, and that's what you're going to have to work with. I will be talking about the work in a paper written by myself, Chris Hernandez, who's part of the PIT Google team, alert broker, and Michael Liu, who is an MIT undergraduate. The paper can be found on arXiv, and it's called the Quadruply Lensed Supernova 2025 WNY Implications for LSST. So let me just read to you. The Quadruply Lensed Supernova 2025 WNY offers multiple lessons on how one might respond to an alert. The full benefits of such rare events are best achieved with immediate spectroscopic and photometric follow-up within hours rather than within days. And I think you can understand why it's so much better to follow one of these things on the way up rather than watching it on the way down. So let me start we give a recipe or a protocol for dealing with quadruply lensed supernovae alerts, and it's simplified, but it gives you the basic idea. First of all, the list has a -1 on it. The -1 is tremendously important. It requires that you work with known quadruply lensed galaxies, what my predecessors here called a watch list. And the idea is that you come prepared with a model based on that quadruply lensed incipient host, hoping that you'll see a supernova there. Now you're going to miss some, as we've heard from Satadru. Okay, but this makes the job of getting it right away easier. So let's look for quadruply lensed galaxies, and I wish Margarita every success in finding 10 to the 7 such things so we can have a good long watch list. Event 0 is the difference image analysis alert. And that's not our department, except to tell you that we have interposed our software into the PIT Google broker. Number 1, straightforward. It's the flagging of an alert based on its proximity to the watch list. Everybody does that. Number 2 is what we call propagation. And that really is the heart of our idea. The idea is that you come with a model. And the model is a model for the lens. The lens is there whether the supernova is there or not. When the supernova appears, you use the model to project, to propagate the supernova from the image plane back to the source plane. Sitting there in the source plane with a dashed line on it is something called a diamond caustic. And if the supernova lands inside that diamond caustic, you get 4 images. And if it falls outside the diamond caustic, you get 2, or in some bad cases, 1 image of the supernova. So we first propagate it backwards to the diamond caustic. We have the model, we know where it's landed in the diamond caustic. We then propagate it forward again to the image plane, and we ask, where are the other images? And if it's inside the diamond caustic, you get the positions of all 4 images. The next step is we call corroboration. And corroboration consists of going to one of the predicted positions and finding another image where it was expected. When you do the corroboration, you don't need 5 sigma because our predictions are very, very good. You'll see in just a second. And if you see something that fast, if you see something that's within a 1/10 of an arc second, and it's fainter, that's it. You've corroborated it. And of course, you might get 3 or 4. So 2025 WNY. Here's what the lens galaxy looks like, a lens host. And it's very faint. It's where this ellipse crosses the hyperbola. They're very faint, but there are two lensing galaxies, and that's the important thing. This was taken 20 years beforehand. Here is the same model, didn't change anything, just moved it parallel, projected onto an image, multiple image taken with the Colibri telescope on October 21st of last year. The next slide is a little tricky. And this is our model. You may have a fast model that you can use. We like this model because it shows you a bunch of interesting things, but okay, use whatever model you have. It must be fast, however. The next slide shows what happens if you put this, any one of the four images is the triggering image. And for each of, assuming each one is the triggering image, we followed it to the other three images. And so in each image, you see a cluster of four symbols, one of which is what happens if it's the triggering image, and the other three are where it came from on the other images. And they're all close to each other. It's a 1/10 of an arc second. Good. What about 2025? Oh, and you'll notice that the lens here is double. So we have a code that does the propagating. It's called, is it 4 or 2 or 1? It's the name of the code. It's publicly available on Zenodo as part of the AS Journals community. Implications for 2025 WNY. Not all lens supernovae are equally promising. So 2025 was triggered on the second day of the discovery season as Wiki Transient Facility. That's a hint that maybe it started to brighten even before this discovery season began, before their first observation. Worse yet, the image that triggered the discovery was the trailing image. Worse yet, the separation between those two images was 5 arc second. That indicates a time delay of months, maybe 3, maybe 6. But everything that was interesting in this supernova happened before the triggering image. And the 2 months of frantic, and I think that's a frenzied follow-up that followed with 8 ground-based telescopes, HST and JWST wasn't going to see very much. Another problem, the lens is doubled. To misquote Will Rogers, I never saw a double lens I didn't hate. Every double lens I've ever tried to analyze has been impossible to model because those two lenses are not barely touching each other with gigantic halos that somehow are aligned along the line of sight. Their halos are mixed up, and those halos have not settled, and so they screw up the images. If you've got a double lens, move on to something else. And in this case in particular, the shear is quite strong, and other investigators have found that as well. And there is a degeneracy between shear contributing to the quadrupole moment and the flattening of the galaxy contributing to the quadrupole moment. And it's a factor of 2 degeneracy in both the time delay and the magnifications. And so while we can predict the positions with very high accuracy, exactly when we predict the order of the appearance of the images, but exactly when to look is going to be difficult for anyone. So let me finish with a personal opinion. Thank you for your patience. Based on 2020 hindsight, which is of course much better than foresight, and that is that most of what is learned from Supernova 2025 WNY will be procedural rather than astronomical. How to respond more effectively and efficiently to forthcoming quadruple lens supernovae. Thank you.
I'm sorry, we are out of time, so we would like to move on to the next talk. So the next talk is by Veena Krishnaraj, and she's going to talk about strongly lensed supernovae in focus, deblending marginally resolved lenses via joint modeling of ground and space-based imaging.
Hello, my name is Vina, and I just finished my undergrad at Princeton. And together with Charlotte Ward, I have also been working on Lens supernovae and Rubin. And as many of you may be aware, we expect to detect many more such systems with Rubin. However, many of them will be only marginally resolved in Rubin observations, which would be quite problematic if we're interested in, for example, studying the time delays between the supernova images, since working with blended light curves to do time delay estimation yields significantly higher uncertainties than with deblended light curves. So because of this, we decided to develop a forward modeling software pipeline that would extract the individual supernova image light curves from combined Rubin data with space-based imaging and estimate the time delays from these light curves. And once we did that, we kind of aimed to quantify within what different spatial blending regimes this works, and also how reliant it is on high-resolution follow-ups. So a quick overview of the pipeline. First, we used a code called Caustics, which you'll actually hear about more in the next talk by Connor Stone, I believe, to generate realistic simulations of systems that Rubin would realistically detect. And then once we had our simulated observations, we used Scarlet 2, a software for deblending to extract the light curves. And once we had extracted the light curves, we used a software called Gauss Ascend or GLIMS to do the time delay estimation. And a little more detail. So we used Caustics for our pixel level image simulations, and we did that for a total of 9 systems that Rubin could detect with varying spatial, spatial separations. So from systems that would be fully resolved basically in Rubin to those that are practically not resolved in Rubin imaging. And we did this in 3 Rubin bands, and we also supplemented this with simulations of Roman observations. So we ran our pipeline using just Rubin, but also including 1 Roman epoch without the supernova in it, as well as additionally including a Roman epoch that does have the supernova, so Rubin plus 2 Roman epochs. So that was our setup. And as for the PSFs, originally we ran this using just simple Gaussian PSFs, but more recently we've been redoing this with more realistic Rubin PSFs from actual detected supernovas with Rubin. The results in this talk are from the Gaussian PSFs still, but so far new results show that there's no decrease in like accuracy when we use the more realistic ones. So yeah, and we have. So now that we have our multi-epoch, multi-band, and multi-resolution observations, simulated observations, we put them into Scarlet 2, which is a non-parametric scene modeling framework. How it works is we have our extended sources, so a lens in a host galaxy, whose morphologies we try to model and whose spectrum is static in time, as well as our images that are basically point sources, but that have a spectrum that's allowed to vary in time. And so we put these together to build a model of our scene. And kind of the most important one of plot over here, this one on the far right, which is the residuals between our observation and our model. This is what Scarlet 2 tries to minimize during the fitting. And as we can see, after we run the fitting, our residuals look pretty good. There's nothing in there, they just look like noise. And we can also then extract the fitted fluxes of our point sources to get the light curves. So this is an example of what they look like. They look pretty good as light curves. And now that we have the light curves, we use Gauss Ascend, which is a non-parametric Gaussian process model to fit these 2 light curves. And in doing so, also fit the time delay between the 2 light curves. And as you can see in this example, we again get a pretty good result. It's only off by about half a day. Now, as I mentioned at the start of the talk, we ran this whole pipeline on a total of 9 systems. So if we look at the results for all 9 systems, generally our pipeline does pretty well. Most sort of interestingly and importantly, we find that when we run it only on Rubin data, so with no Roman follow-ups, we still get pretty accurate time delays with errors of about a day or less than a day. Same goes for the separations between the images. We get decently accurate separations even without supplemental space-based follow-ups. However, although these results are good, there is, even without using Roman, there's a caveat to this, and that is the morphologies of our extended sources. As you can see, if we fit without using Roman, what we end up with are just kind of blobs that are not meaningful. So we do need space-based imaging to sort of ground the modeling and get these sort of accurate more complex, like extended structures like the lensed host arc and so on. And finally, as I mentioned at the beginning as well, sort of point of all this deep blending is because using deep blended light curves is supposed to give better results, but we wanted to sort of test that. And so we use an extension of Gauss's Sen called Glimpse that is semi-parametric. It uses a light curve template, but it's still a Gaussian process model. And when we run it on the deep blended light curves, most of our errors are on the time delays are below 1 day, while with blended light curves, if we give it a sort of sum of the light curves, we get errors that go up to 2 days. So indeed, deep blending improves time delay estimates. So overall, we can get pretty accurate photometry and time delays using this framework and using only Rubin data even in pretty blended Rubin scenes as well, which is great news because that means we don't necessarily need high resolution space-based follow-up for every single supernova detection. What we could do instead potentially is use our Rubin observations for the time delay estimations and say use even archival space-based imaging for the lens modeling and combine the two. And in general, what would be great is if we could implement this into the overall Rubin pipeline. Once we start getting more alerts for potential lensing systems, and if they're pretty blended, we run them through our deep blending pipeline and see what light curves we get out of that and what we can do with them. And ideally, if they're supernovas, do time delay estimation on them. And actually, this is not a Rubin detection, but currently our code is being used on the supernova that was just talked about from 2025. So this is an example, sort of current plots from Scarlet 2. And these are the residuals. They're looking pretty good. So yeah, that's currently in the process of being done. So thank you.
Hey, Veena, nice talk. Can you go back to the light curve that you showed? Yeah, so next slide, please. How sensitive is this to the cadence? Because you have a really high sampling of points there, which is surprising to me actually from Rubin, and also really only the single band, but both the images. Did you simulate UGRIZY?
We simulate, that was in the PSF side, but we did GRI. Those are the 3 Rubin bands, and we also picked 3 of the Roman bands. So we have 3 bands that we simulated at the same epochs. And as for the cadence, I think this cadence is approximately 6 days-ish. So I don't think it's that, maybe a little bit more peak, but yeah, we didn't do that high of a cadence. I was actually thinking of adding more points, but if you think it would be good.
I think it'd be useful to take a baseline OpSim and just use the cadence directly from that. And just seeing that your time delay errors aren't overly sensitive to the choice of cadence. And if you have GRI, and you folks can extract the light curves and classify them, you might even be able to get even better time delay accuracies if you know the class of supernova, since we know the behavior.
Yeah, that is true. It's if we know, as I mentioned, we do Glimpse assumes a template, and it does give better results. So if you know the class of the supernova, it would be even better to use Glimpse with the template. But it's sort of, if we're not 100% sure about the class, Gauss's Sen is better since it's non-parametric, and it still yields good results, just depending on what your priorities are and what you know.
Yeah, great talk. Could you put up your morphology slide again for a second? Yeah, the one after.
This one.
Yes, morphology trade-offs. Yeah, you're getting the improvement just because Roman has space-based resolution, right? That's the only thing that matters there.
That's the main difference, because these are systems that are not fully this example system. Let me find it. Is I think that one. So
Okay.
As you can see, it is much more blended in Rubin because the separations are below the seeing of Rubin. So it just cannot extract that, but you do still sort of see the arc-like structure in Roman imaging. So yeah, it just basically uses Roman because it's fitting both at the same time when you give it both observations. So.
Okay. All right. Thank you. That's great.
All right, so in the interest of time, we will move on to the next talk. So Our next speaker is Connor Stone, and he's going to join us online. And he's going to talk about caustics software, I think. That's what we're going to hear him from. Yeah, so Connor, yeah, take it away.
Thank you. Yeah, thanks for having me come talk about caustics. And I should say thanks to Veena for the shout out during her talk. My plan was really to advertise caustics, but I think the best advertisements are people doing cool science with these codes. So that's great. You all got a preview of what you can do with caustics. So I'll go quick over this. Gravitational lensing, as everyone I think in this room knows, is a really sensitive probe for a lot of cool different science tasks. But a lot of these with modern data sets, there's a lot of data to process, and you want to do it at really high resolutions, and you want to do very detailed modeling of all the factors in there. So you need a lot of compute to throw at modern inference problems. And that's where caustics comes in. So we've basically from the ground up built a gravitational lensing simulator. It's fully featured. So anything you think of related to gravitational lensing, whether it's time delays like Veena had, detailed convergence maps and source image maps, getting critical curves or caustics, as the name implies, forward ray tracing, all of this is possible in caustics. And thanks to Jackson PyTorch, it's fully GPU accelerated and auto differentiable, which really plays a big role in the kinds of problems that you can approach with a code like this. We've done our best effort to really make it detailed documentation and tons of tutorials. We've got a live playground on the website where you can just start using caustics and twiddle around some parameters and see what happens. There's a little Easter egg in there. If you go in, you can upload any image you want and gravitationally lens it, which is fun. Like we've got an introduction to gravitational lensing using caustics and all sorts of tutorials that teach you all the individual elements of what you can do with caustics. I mentioned that it's GPU accelerated, and that's what this plot here is showing. If we're just trying to say we're trying to do some sort of like simulation-based inference where you need a ton of simulations of different gravitational lensing configurations, then you really just care about how many samples of simulated lensing images you can pump out in a given chunk of time. And so here we have the number of samples on the x-axis, the amount of time in seconds, and we've got caustics running in a few different modes. The blue line here at the top, that's Lenstronomy, super widely used gravitational lensing package out there that's very powerful. And it runs on the CPU. And the CPU version of Lenstronomy runs about as fast as the CPU version of caustics. They would sort of trade places while I was doing this testing, so they're about the same speed. But this purple line here is the runtime for a GPU. And you can see that the runtime doesn't increase until you saturate the GPU. And that saturation point, and from that point on, so generating 100 examples or more, caustics is about 1,000 times faster, which is pretty incredible. And this is what lets you do the sort of source modeling or forward modeling that Veena was talking about. We did some in our own group. This is work by Ronan Leggin. You take a proposal for what the source could look like, use caustics to gravitationally lens it, take the difference of this model with your observation, and there's a likelihood. We can use diffusion models and score-based modeling, which is a variation, a way to do posterior sampling. And so we get really high likelihood, really realistic samples from this. Comparing to some like previous works on the same lens, we were able to get like way more detail and more realistic and better likelihoods for doing this sort of framework. And a lot of it comes down to the fact that we could just throw tons of GPU compute at this problem and auto differentiate through it to get gradients in the high dimensional inference that we were doing. I mentioned that it's a posterior as well, so it's really cool as you can get posterior samples of what the background source could look like. These are all sort of like realist. Every single one of these produced the kind of residuals that you saw before, where it just looks like we've completely subtracted the source from the sky, which is super, super neat. And we're not just doing source modeling, we're doing some AGN microlensing stuff with the people in the Future Lens collaboration, which you can see up in the top. And this is really, really cool, but also super intense for computing needs because you have potentially thousands of point masses that you're trying to model the ray tracing through, where you get all these tons and tons of caustic lines on the source plane that all are all overlapping with each other. But you get these really cool time domain light curves of what the AGN could look like. And this lets you do, once this thing is fully online and we're like really cranking it through, we're going to be doing some simulation-based inference on the kind of light curves that of AGN that come out of Rubin and get some information about what's going on right down to the disk, which is up at the top here, the disk around the black hole. So that's going to be really exciting time domain stuff. I didn't have a picture in it here, but there's also some gravitationally lensed supernova stuff that I've been playing around with. So I'll thank you all for listening. I hope you go check out Caustics and make a gravitationally lensed profile picture for yourself. And I'll take any questions people have.
Are there questions for Connor? Maybe I can ask one. So thanks very much for showing these cool simulations. I wanted to know whether you have tested the caustics for much larger lenses or like more massive, like for like groups and clusters.
So I haven't tested it on those myself, but the way Caustics works, you can query it on a grid of coordinates, which is what we were doing for a lot of our analysis, but you can also be really selective about what coordinates you're querying the ray tracing for. So it can totally scale to those really large images where you want to be a little more focused about where you're sampling your image in order to keep the compute requirements in check. And actually, we have a demo of that in the tutorials on the website. It's basically just for a regular galaxy scale gravitational lens, but we show how you can focus your compute right where the multiple images are. And the same thing would apply for a big cluster lens, where you want to focus your compute where your multiple images are showing. Exactly.
Okay, thanks. Any other questions for Connor?
Very trivial. Thanks. I'm sorry, is that Jean-Luc Picard on that last slide?
Possibly.
It is Jean-Charles, and he's working more on Euclid side, but doing some really cool stuff. Yeah.
Okay, because you got to put that picture side by side with Patrick Stewart on the Star Trek: The Next Generation. That is amazing. Thank you.
This reminds me so much.
Okay, we may have some more time in case anyone wants to ask one final question.
Modern
Okay.
Well, instead of asking a question, everyone go check out the Caustics website.
I guess we will do that after the session. Okay, if not, let's thank Connor and okay,
Thank you.
so we're going to have the last talk of the session by Aisu, and she's going to tell us about search for dark matter with strong lenses.
Okay, so hi everyone, I'm Aisu, and as a graduate student, my research on dark matter problem in general. And one of my projects is based on LSST's strong lenses. And in this talk, I will be focusing on the LSST's impact on dark matter and dark energy physics under some factors such as satellite contaminations. So we can classify gravitational lenses into static lenses and variable lenses. Static lenses mainly probe the dark matter properties. Meanwhile, variable lenses can address questions related to both dark energy and dark matter. LSSD is expected to discover hundreds of thousands galaxy scale static lenses. Meanwhile, only a few thousand variable lenses. And although we are all excited about the advancement in these fields with LSSD, we are facing a serious problem, which is contaminations due to satellite trails. And variable lenses are in greater danger compared to static ones due to the scarcity of their numbers. So contaminations occur due to the reflective parts of the satellites during the twilight time. Here you can see an image from HSC and a simulated satellite streak as a Gaussian function. And then you see a simulated strong lens here with a satellite streak on it. So in this project, I have other questions, but one of the questions that I want to discuss is how do contaminated exposures affect LSSD's contributions to strong lensing science? And in particular, what is the impact of removing contaminated exposures on high accuracy time delay measurements with LSSD? I will try to address this question in two parts. At the first part, I will be showing you some results from contamination simulations in OPSIM observations. And in the second part, we will be looking at light curve simulations and some tests about like exposure removals from those light curves and how it impacts our time delay measurements. So this is our methodology for the contamination part. We use SkyField to simulate the orbital positions of each Starlink satellite using the TLE data, and we use Mossad package to simulate the brightness of those satellites at a given point in time in the observatory sky. For LSSD observations, we use OPSIM, and for manipulation of those images, we use LSSD science pipelines. That was supposed to be a video, but okay. So at this part, our target list is basically now confirmed and candidate strong lenses from SLATE database. And we focus on the Euclid Low-Dust region of the LSSD's footprint. So we mark the contamination events as follows. You can see the exposure field of view with blue circle. And then in our simulations, we track all satellites having a trail through the exposure region. And if those trails meet certain criteria with a chosen target here, we mark this target as contaminated. Here's a larger scale of the contamination events, and the colors of the trails shows the brightness of the satellite at this position. So from the visits point of view, we see that more than a quarter of twilight visits contain satellite trails, and almost 1/3 of those visits have contamination of one of our observed targets inside of the field of view. And from the target side, we see that depending on the region that you are focusing on the LSSD's footprint, 4 to 6% of all targets are contaminated at least once. And if we also include the contaminations near to the field of view, but not inside of it, the number goes up to 34%. And at this point of our work, we basically discard the exposure that is contaminated since it's much brighter than the lens. And in the second part, we simulate supernova lenses with 2 images and 4 images using lens SSD. In lens SSD, those light curves are injected into OPSIM, and with a module that I added to this package, I can track the twilight exposures. And in the second part, we take those light curves with twilight exposures on it, and then we fit the whole original curve to estimate the time delay. And then in the second step, we remove one of those twilight exposures and fit it again to measure the time delay again. Basically, we repeat this procedure until we have no time delay twilight exposures left. So this is our population statistics for 2 image lens systems. We have these main conclusions, which is more exposures means higher accuracy time delay estimations, and those systems are less likely to have less pre-peak exposures, which means the number of exposures before the supernova happens. And in the top row, first column, you see that the effect of removing one single exposure from various light curves. And you can see that the shorter the light curve is, higher the decrease is on the accuracy of those time delay estimations. And the second column, you can see that removing 3 twilight exposures can also affect even like longer light curves accuracies. We see similar trends in both population statistics and exposure removal tests with 4 image lenses too. And to conclude, we all know that LSST will have a crucial impact on both dark energy and dark matter science, but this impact is threatened by satellite contaminations, and especially variable lenses are in greater danger. And even in this relations that we made in the first part, our contaminated targets included 4 variable lenses, and if these variable lenses are not long enough, as we have shown, they will be they will be negatively impacted by the removed exposures. And yeah, I think that's all. I can take your questions, and thank you for listening.
Questions?
Thank you for your talk. This is very important work. Have you been in touch with like Meredith Rawls and all those other people who are talking to Amazon, Leo, and Starlink and SpaceX to make sure they know this information?
I know, I'm familiar with their work from AAS mainly, but I haven't discussed my work with them. So basically this work is still ongoing and we have a paper in prep. But yeah, surely eventually, maybe in the next AAS.
Well, Meredith is here at this meeting, so absolutely send her preprints, and make sure she knows this. This is incredibly difficult. But on the more science side, if those variable lenses are gone, do we think you'll be able to achieve any significant scientific results through the LSST? Are you going to wind up like not the objectives?
So the thing is, during the whole course of LSST's observations, we will see like a few thousand variable lenses, and only up to 1,000, less than 1,000 of them will be SN type 1A supernovae, which is the group of variable lenses that we expect to achieve the highest accuracy. And this is important because we already have some confined value for the Hubble constant, for example, but we need higher precision or higher accuracy. And to do that, like those supernova observations will be quite important. And from our simulated light curves, among the whole population, for the baseline curve with no exposures removed, only 20% of those light curves gave us better than 5% accuracy. And among those, like more than half of these have short or moderate light curve lengths, which means they are sensitive to any removals. So basically, you are taking, let's say, 1,000, say like 20% of this, but you have like 200, and among 200, there are like previous work has shown that you need. They usually choose golden samples, which means you need that like a certain fraction before the supernova peak, and then you need you need a certain fraction to be after the peak, and then you need like band or number of image constraints. And when you add all of these from like 200 supernova lenses, you will end up even fewer. And then if a satellite ruins one of the exposures, then your accuracy drops. And then even if you have like the second contamination, then you basically lose it. And this is just for Starlink satellites, and it is for the population of satellites at this moment. And we expect to like the number of satellites to increase more and more over the course of 10 years, and it will get worse, unfortunately.
Thank you.
Right. So with that, sorry, there is one more question.
Just a
Okay,
comment.
let's have this one.
Yeah, just to answer your question, I'm LSST chief scientist, and we've been working with SpaceX on this. They understand the issue, but the big problem is the ultra bright satellites that are going to be launched, and that's incompatible with this. But they understand the impact here.
Okay, so with that, I would like to thank all the speakers and all the members here for an interaction. Thank you, everyone.